For many, life in the United States means freedom. And this is generally a good thing, except when it means freedom from having to change in order to even be conversant on an issue that's been embraced by the rest of the world as something great. You might think I'm talking about soccer here, but I'm not. I'm actually thinking about the metric system. The average U.S. citizen knows little else than the English units of measurement that are ingrained into our minds from an early age by constant usage. We grow up measuring our heights in feet and inches, our weight in pounds, and our temperatures in degrees Fahrenheit. We dispense gasoline into our cars in gallons and estimate the sizes of our fields in acres. The problem, and there really is a problem potentially brewing here, is not that the English units fail at what they do. Sure, it's awkward to have to go through the mental math required to convert between feet and miles. And by the way, it's 5,280 feet in a mile. It's far easier to convert within the metric system. 1,000 meters, for example, is a kilometer. But lack of convenience is not a fatal flaw. And if it were just the United States and nobody else, there would not be a problem, except from those sketchy conversions between the units. The real issue is one of communication across a globalized human population. Historically, there have been many different systems of measurement. The dimensions of the Great Pyramids of Egypt and Noah's Ark are both described in cubits. Traditional Chinese units of length are chi, bu, and li, whose actual values varied historically according to the dynasty and geographic region. Each isolated culture has probably had its own system for measuring length and weight that worked well enough for their purposes during their time, but the need for a common standard system became evident as life became modern. In order to be fair, an international system would not be based on any one culture's pre-existing set of units, which were often based on something totally arbitrary, like length of someone's arm or the amount of weight that a soldier could carry. The units of our metric system were originally designed to be things that would be the same no matter where on Earth you are and when on Earth you happen to exist. For example, 1 liter of pure water is exactly the same as 1 kilogram of pure water. Water is something you can find anywhere, at least as long as you're somewhere on the Earth. More recently, these units have been standardized in a way that would make them universal. That is, not limited in validity to the surface of the Earth. For example, 1 meter was originally defined as 1/10,000,000th of 1/4 of a circumference of the Earth taken through both poles. But because the Earth is not perfectly uniform in shape, there had to be a specific quarter circumference path to define the standard. And so the General Conference on Weights and Measures decided that it would be the distance between the North Pole and the equator through Paris. That's the precise distance, 1/10,000,000th of which would be the definition of a meter. In the image shown here, that specific quarter circumference is shown as 10,000 kilometers. How many meters is this? The original proclamations for an international system of measurements, the SI units, where SI stands for Système International. These proclamations were made in 1875, but in the time since, we've replaced the definitions with something that's more standard. 1 meter is now defined as this number, 1/299,792,458. That number times the distance that light travels in 1 second. The speed of light is a universal constant, so it doesn't matter where you are, a meter defined as such will always be the same. Now you might have noticed that this logic requires that the second, that is the unit of time, also needs to be defined as something more universal than 1/60th of an Earth minute, which is 1/60th of an Earth hour, which is 1/24th of an Earth day, which is based on the speed of rotation of the Earth. So this has also been standardized as 9,192,631,770 cycles of a cesium atomic clock, And this would also be exactly the same wherever in the universe you and your atomic clock happen to be. Yes, there's a lot more going on behind the scenes for concepts that you use every day without thinking. You never have to think about things like, what is a second? In this lab activity, our first, and welcome to the class, by the way, we're accomplishing two things. First, this is an introduction to the basic metric units, as well as the methods and tools that we'll use to measure things as part of our lab activities throughout the semester. In addition, it's also a data gathering session to support our second lab next week on the scientific method. This video is a walkthrough for this week's activity. Now, if you're taking in this video as a pre-lab assignment/quiz, that is with play pause it, the playback is going to pause at different times, at which point you'll be required to answer questions before you're allowed to advance the video. So this won't happen if you're viewing the video from YouTube directly. You should read the written handout in its entirety before moving forward, as some of the questions you get will require information that's available there that is not necessarily covered in what I'm saying in the course of this video. You'll have only one shot at answering the questions, and yes, your responses will count as your answers in the pre-lab quiz, so you don't want to be guessing. In the first week, you'll be following the lab handout's written instructions and carrying out a set of tasks that require you to practice measuring things with the metric units, thereby developing familiarity with both the units as well as the methods. For length, you'll use a meter stick, also a metric ruler, and also a microscope, in which you'll be estimating the dimensions of a cell based on the known size of the field of view. For measuring mass, we'll be using an electronic balance. Now, over the course of the semester, we'll be using graduated cylinders a lot to measure volume in the course of our lab exercises. We'll also be using a lot graduated transfer pipettes, which are disposable plastic droppers with gradations embossed on the side. And we'll also be using micropipetters for the dispensing of really tiny volumes. In this part of the lab this week, we'll be completing an exercise in which we compare the accuracies of different volume measuring devices. The fourth and last kind of measurement we'll carry out this week will be of temperature, and the tool we use is the basic familiar thermometer. In addition to developing your basic skills in measuring things with accuracy and precision, the written handout will also have you converting between different units of measurement. Also, for the part of the lab where you compare volume measuring devices, you'll be tasked with evaluating your results and validating your conclusions with appropriate argumentation. You'll record these data and analyses into your lab notes for week 1. Don't forget, we'll also be using these results next week in a graphing exercise. Speaking of next week's lab, we'll spend some time toward the end of the lab generating a class-wide data set on human body measurements. Yes, on ourselves, and entering the data into an Excel spreadsheet. This data set will be an important part of next week's lab on the scientific method. In the first week, it's mostly carrying out steps and filling in answers in the empty spaces of your lab handout. There's not a lot of open-ended lab activity that requires special effort for documentation in your lab notes. This will change next week. You're getting off easy with a lead-off lab exercise. Still, do make sure that you've completed the lab handout with appropriately thoughtful responses to all of the questions.